Greetings, fellow learners. In this video, we are going to visualize the deep layers of convolution neural networks. So we'll begin our discussion by understanding why we want to do this. So this here is AlexNet. It was in 2012 the state of the art for object recognition, where you pass in an image and you'll get a class categorization of what this image represents. And throughout this, we have a sequence of convolution, activation, and max pooling layers, followed by some feed-forward, densely connected layers. Now, in order to visualize exactly what these represent, let's say that, to this network, we have maybe an image, like an MNIST digit 7, that we pass through the first layers of the network. And then what we can do is just visualize the activations of the feature maps. So when you pass in that 7 at the feature map for the convolution layer, let's say that there's 8 of these feature maps, you might get some things that look like this. Very red and very blue means that the filter has picked up on these patterns. So you can see that, okay, maybe each of these filters is kind of picked up on the stroke of the 7. Maybe this is picked up on some other inner edges and inner shadows of the 7, and so on here. And this is for the convolution layer, the activation layer, the pooling layer. And I guess at this point, you can kind of see visually what the feature or that filter has learned. But as we go to the next block, the next set of convolution, activation, and pooling layers, well, it's really hard to kind of understand really what's being learned here. And so kind of the point of what we want to do now is there a better way to actually visualize what the internal architecture of AlexNet and some of these deeper architectures has learned? Because it can give us an insight into whether the training has actually happened correctly or not. And it can also, as an added benefit, guide future neural network research instead of making it all about some trial and error for some network components. And so all of this is kind of why we want to effectively visualize the internal components of a network. Now that we understand why we want to visualize convolution networks, let's understand how to visualize them. So let's consider this layered architecture of a convolution neural network with convolution, activation, and pooling, feed forward, and it's trained in visual object recognition. Now, let's say that we want to visualize what this layer has learned. And instead, before we would, look at just the activations at probably this point over here, instead of that, what we're going to do is, from this forward pass, we're going to actually pass this here into a max unpooling layer to undo this max pooling. We then pass it through a relu activation, and then we undo this convolution operation with a transpose convolution operation. And we keep working our way back to the beginning of the network until eventually we will get a pixel space activation from layer N. And what this will represent, it is the visualization of what this layer has actually learned to focus on. And so that's kind of our goal and how we want to visualize. Now, let's get into some of the details of exactly how we can visualize this with some computations. So let's just consider a very simple network of 5x5 input. It has 2 filters of 3x3. And after you apply a convolution, you're going to get an output feature map. We have 2 feature maps over here. Then we can apply relu activation, and then we can apply a max pooling to get the pooled outputs. And then there's just next layers. We're not concerned with this for now because let's just say we want to visualize some components here. So let's say in here that the input to this, after, let's assume that this is a trained filter. These filters are their final weights. It is inputting an image that looks like an A. Then when passed through the convolution layer and we apply the convolution operation, you might get something that looks like this. So basically you can imagine, take this, it's a sliding window approach that we go over here, take a sum of these products and put that over here. Similarly, slide that window and do the same thing. That's the fundamentals of the convolution operation. Next, what we're going to do is perform a ReLU activation, which will clamp all the negative values to zeros, just to highlight which are like the active neurons. And next, we perform pooling, where we have a window size here of like 2 and then a stride of 1. And we're just going to perform like a max pooling operation. And the outputs are just over here. Now, let's say that we want to visualize what this max pooling layer has actually learned. And so what we're going to do is first, we're going to create something called like some switches. And this is going to be used eventually to unpool or to reverse the pooling operation. And what we do is, it's a function of whatever this pooling output is, that's 0.6, 0.4, 0.6, and 0.2. And during the forward pass, we would have actually recorded like which position that, what actually created this. It's kind of like an argmax. So 0.6 was created from position 0. 0.4 was created from position 1. 0.6 here was created from position 6. 0.2 created from position 4. So this is position 0, that's the 0.6. This is the position 1, which is the 0.4. Then position 6, that's this 0.6 that created this. And then you have the position 4, which is this 0.2, which created this over here. And now that we have these switches, and we also have this max pooling output, we can try to reconstruct what its predecessor was. And so you can kind of get this 3x3 grid where we have, this 0.6, 0.4, 0.2, and 0.6. So this is kind of how we can reconstruct it using these switches because we know what positions they exist in. And everything else is kind of zeroed out. And so this is kind of like a lossy reconstruction of what this layer was. Next, we are going to, create an activation here. So it's kind of like a no operation as there's nothing below 0 and everything is clamped to 0. And then now we perform transpose convolution. And the way we do this is, let's say we take this right over here, and we know that, and we also take this, neuron here, it's 0.6. This neuron would have been created from the neurons that are present over here. And in order to kind of determine like what values they should be, you basically multiply each of these values here with this 0.6. So that's 0.6 times negative 0.2, you get negative 0.12. 0.6 times 0.2, you get positive 0.12, and so on. Next, you do the same with 0.4. With 0.4, what we're going to do is now it's going to affect the neurons over here, and we take the product of this neuron along with all of these neurons over here. So that's like plus or minus 0.4, which we will add or subtract to the neurons here, and you get something like this. Then everything else is like 0, so plus or minus 0, nothing changes. So we'll go to the next non-zero neuron, which is 0.2. And this would mean we add, if you multiply 0.2 with all of these other plus or minus 0.2s, you're going to get plus or minus 0.04, which you add or subtract to the neurons over here. So you take this 0.6, you multiply it by like the positive negative 0.2, you get 0.12 positive or negative, which will affect the neurons over here. And when you add or subtract those values, you'll get this. So effectively, now this is going to be the pixel space activations for this max pooling. So this effectively we've represented it in the pixel space that looks like this, which makes it easier for us to now visualize. And if you try to even like code this out, you can code this out with like torch functions like max pool 2D, max unpool 2D, ReLU, and then you perform the transpose convolution 2D, and you print them all out. You'll notice that the final output is exactly as we computed them. So I hope this makes sense if you also want to verify it with code. Now what we can do here is use those core components in Torch, and we can also now take AlexNet, the trained architecture, pass in an image to the architecture, and visualize, let's say, each of the convolution layers along the way, mapping them to the pixel space using this deconvolution computation. And in doing so, you'll get like, this is the original image of the tiger. Maybe there's like some grass and some like water in the back. And if you pass this into like the first convolution layer and try to visualize what that convolution, feature map has learned, there's many of these output feature maps. I'm just going to display like 16 of them, where we basically see that, the green is considered the points of activation. So you can kind of see that like for this convolution layer, it's focused a lot on the outline of the tiger. You can see some of them are focused on the river that exists in the back. There's also a lot of like edges that are being highlighted on the tiger, which whether it's like the stripes or like the actual contours of the tiger itself. So you can see that this first layer has kind of detected some edge sense of like edges. And this is just the feature map without the overlay of the image itself. So you can actually see like the edges being detected. Now for the next convolution layer, after the convolution activation pooling, there's another like convolution layer. We can see that, there is like some emphasis on detecting the background, and also some emphasis on, some of these are detecting like the face of the tiger itself, the foot contours. And a lot of it is actually detecting parts of the actual conceptual object too. So that kind of makes sense. But then as you go to like the higher layers, admittedly, it gets a little trickier to see like what it's focusing on. There are parts of like the background that I think the network is now, or these like specific convolution layers are focusing on. And it also just gets more abstract as you go further down as well. So while this is actually a nice visual representation for a single input sample, it gives like maybe some general guidance of like, anecdotally, is this network kind of learning well? But we can actually do a little bit better. So this here is like a visualization that's a part of the main paper that introduced this deconvolution for visualization specifically. And I'm just going to walk through this to get an understanding of like what the layers are truly representing. So let's say now that you have AlexNet and it is a fully trained network. Now we take an entire validation set, which may be like tens of thousands of images that we just pass into the network. And for each case, we will record the output feature activations for every filter in every layer. Now, for each of these convolution layers, there's going to be many feature activations because there's many filters. We're just going to choose a subsample of, let's say 9 or 16 of them. And for each of those feature maps, we're just going to choose the images that led to the largest activations and then try to paste it on screen here. So effectively, if we're looking at this here, each of these consider that for layer 2 convolution layer, we are viewing the outputs of 4 cross 4, so that's 16 feature maps, some randomly selected feature maps. Now, for each of these feature maps, we are looking at the top 9 images that activated that feature map the most. So these are like 9 images in the inference or validation data set that activated this specific feature map the most. And the idea is that, if we look at these images for one feature activation of the convolution layer, and we also look at this corresponding pixel space maps, we'll get a good sense of understanding of what this specific filter or feature map is specialized in recognizing. So let's go through some examples. So in the first convolution layer, we're looking at some random 9 feature activations. And you can see for each feature activation, it looks like it's paying attention to edges. And specifically, all of these edges for a feature map are kind of oriented in the same way. These are all 45-degree diagonals. This one's 60-degree diagonal edges. This is the opposite side diagonal edges. So they all pay attention to some sense of orientation. And you can also see that there is also some sense of color that's picked up by the layer 1 convolution feature activations. Now let's move on to layer 2. So here we are visualizing 16 feature activations. And of these, for each of these 16, we're looking at the top 9 images. So let's say in this, we can see that there's a good sense of color that is detected by this specific feature maps. And some of these feature maps also are good at like detecting some form of like pattern or texture here. There's also like some that detect, these directional edges, like vertical edges in some sort, or they're also like circular patterns. And so you can kind of see at a high level that these layer 2 feature activations specialize in detecting like colors as well as patterns. Now let's go on to layer 3. So with layer 3, we're visualizing this is 12 feature maps. And for each feature map, you can kind of see, let's say this first feature map looks like it's detecting like a good amount of these patterns, like this mesh type structure. And you can see that this one over here is kind of detecting more like circular objects. And let's see, this here is detecting, it looks like it's highlighting this entire structure here. So that looks like the back, but it's not actually recognizing this as the back of a human, but more like just the contour or, kind of like the curvature right here. So it is kind of still paying attention to general like curved shapes. And looking at, let's say these patterns over here, it's activated with some of these like words or like barcode symbols. So it is starting to detect like some form of like texture as a whole. So there's a lot of like texture and certain shapes that are being detected in layer 3. So this is slightly higher level conceptually than like the color or edges detected in the first 2 layers. So that looks pretty nice. Now going to layer 4, things get kind of interesting because this is where we're actually starting to see some more conceptual understanding. So with layer 4, you can see like this first feature activation. It looks like it's detecting, a dog face or what kind of looks like, 2 eyes, a nose, and a tongue, basically. And if you go over here to, this part of the image, it looks like it's actually detecting, looks like it's activating from like the reflections that you see in water. This feature map looks like it's been activated through like 2 legs, and it's learned to like recognize 2 legs. And so overall, we can see that layer 4 tends to have a much higher level of conceptual understanding of objects than the previous layers. Now, moving on to layer 5, this one's pretty interesting. So here we see like maybe this feature map is looking at a lot of different kinds of patterns, like a dotted pattern, and it's activated by that too. Now, what's interesting is that there's probably nothing that looks really in common for this particular feature map. All these images look very different. So it's really hard to kind of tell what this specific feature map is trying to learn or has learned. But if you look at like the pixels, the pixel activations here, you can kind of see that, this is the grass over here. Similarly, this center part is also grass. So it almost looks like this feature map was actually picking up on the background grass itself. And now we have this feature map that looks like it's picking up on some signs. And this one over here looks like it's picking up on the general like contour faces where we have like, an oval face along with like 2 eyes and a mouth. That's why it probably groups like humans and dogs together. But it is also pretty good at detecting, these dogs with like pointy ears and also at detecting eyes itself. So overall, we can still see that the layer 5 looks like it has even a higher conceptual understanding of the objects than like the previous layers that came before it. And so these layer 5 filters are looking at much higher level data compared to, let's say, the colors and orientations of layer 1, the edges and patterns of layer 2, the textures and some color of layer 3. And then, some higher level conceptual visuals of layer 4, whether it's like water or, the legs, or even just like full objects on layer 5, or even like sometimes like the background, like grass. And so I hope that this gives intuition on how, like what exactly these feature maps are learning in the internal layers, and also how, as we go deeper, how these features change. Quiz time. Have you been paying attention? Let's quiz you to find out. Which of these is false about convolution networks? A. Deeper layers better understand objects conceptually. B. Earlier layers detect low-level features like edges and color. C. Earlier layers better understand objects conceptually. Or D. Earlier layers are more invariant to image changes. I'll give you a few seconds to answer this question. The correct options are C and D. Did you get them right? Leave your reasoning down in the comments below and let's have a discussion. And at this point, if you do think I deserve it, please do consider giving this video a like because it will help me out a lot. Now that's going to do it for quiz time and this video, but before we go, let's generate a summary. So we started out this video by looking at the output activations for a neural network and just understanding that, some of these later layer activations are just not easily interpretable, and hence we don't really know if the neural network was trained properly. And so to get around this, what we could do is that if we wanted to visualize, let's say, the output of this layer n, we could perform an unpooling ReLU activation and transpose convolution in series until we get pixel space activations from layer n. And this pixel space activation is going to visualize what layer n has learned to focus on. We also looked deeper at the computations that are involved in actually computing this as well. We then took a look at all of this in action by taking a trained AlexNet network, passing an image into the network, and just for every single convolution layer, we basically tried to map it back to the pixel space so that we can actually see which parts of the image are being activated. Now, while this doesn't give the entire picture, it can at least directionally give you a sense of if the network is kind of being trained, at least with a single example. And then we concluded by understanding exactly what every layer of an AlexNet architecture is learning, from the edge level features of layer 1 to much more higher conceptual features in the later layers. And that's all that we have for today. Thank you all so much for watching. Some of the code and the resources for this video are going to be available in the description below, including some of the slides and the computation. So if the numbers were too small, you can look at it later. Thank you all so much for watching, and I will see you in the next one. Bye-bye.